Hi, it's Yatin, and I'm going to talk to you about geometry, Euclidean and spherical geometry. So basically, Euclidean geometry is the geometry that we've all been taught in school, and it's called Euclidean geometry because it was first postulated by Euclid, and it's been stood the test of time about 2,300 years. So it's based on his 5 postulates, and all of the geometry that we use is true to these postulates. So the first postulate is that for any 2 points that we draw in space, then there's exactly one line that will intersect both of them and go through them. So then his second postulate is for only 3 points that are not on the same line, there is only exactly one plane that goes through all of these points. His third postulate is that if there's only 2 points are needed to define one line, so if we have a look at this line, if we have 1 point here, we only need this one other point to be able to define a line in any direction in the plane. His fourth postulate is that any 2 right angles are congruent, so no matter what orientation, these 2 right angles will all be the same in space. And his fifth postulate, which is probably the most important postulate, is that given any line at a point, there is only one line that exists that is then parallel to this line that goes through this point, and there's no other line that exists which satisfies that condition. So Euclidean geometry is basically the geometry that goes and sorts of fits all these axioms, and most importantly is this parallel postulate. Non-Euclidean geometry is basically geometry that uses a different set of postulates that Euclid defined. So spherical geometry, when we come onto that, it's the idea that instead of having a plane and looking at geometry in this plane, a plane now becomes a sphere, and what happens like in and around the sphere in 3 dimensions. So now we can check Euclid's postulates against the idea of it being a spherical geometry, and we can see a lot of them are true. So if we look at the first postulate, if we have our plane, we have any 2 points, there does exist one line that goes through them. It also comes back around the other side. And then so Euclid's first postulate is true. If we look at the second postulate, it's that if we have 3 points, then there's only one plane that there can be, and this is that plane right there. It's on the sphere, and we can't draw any line that connects all these, one straight line that connects any of these 3 points. It's just the plane. So that's also true. And then the third postulate is that we can look at this diagram and see if we already had this point, we'd only need this other point or any other point on this line to define that unique line. So that's also true. And then if we look at the fourth postulate, it's that right angles are congruent. So if we look at him, right angles look a bit obscure in spherical geometry, but if we connect them like this, you can see that these 2 lines are these 2 points are any perpendicular lines and any right angles are congruent in space. The problem is that for spherical geometry, right angles sort of look like this and look a bit odd, but they are all congruent in space, so that's also true. And then the fifth postulate, the problem is that if we have a line, and given any point, there is no line which exists such that there's a line that goes through this point that is parallel to this one and is also a straight line. So the problem is that the fifth postulate is not true in spherical geometry. So there are also some strange properties of spherical geometry. One is that 2 straight lines will always intersect in 2 places. So we have a straight line like this, come back to the side, a straight line like this, come back to the other side. They intersect in this place and that place. So normally in Euclidean geometry, straight lines will only intersect in one place ever. Here they are intersecting in 2 places. The second strange property is that if we have in Euclidean space, if we have A, B, C, we can say that this point B is between A and C. However, in spherical geometry, if we draw a similar straight line and put A here, B here, C just round back here, we can say, yeah, A is between B and C, but also B is between A and C, and C is between B and A. So the idea of something being between something is quite different in spherical geometry because everything's sort of between everything else. And the last, probably most weirdest property in spherical geometry is that triangles can have greater than 180 degrees length. So if you draw a triangle here, a straight line might look like this. Sorry, that line should go that way. And then, so this triangle in spherical geometry can have more, the sum of the angles can be more than 180 degrees. A classic example is if I started at the North Pole, walked down to the equator, walked across the equator, and then back up, we can see that these two angles here are 90, and whatever angle this is, we're going to have 90 degrees, plus 90 degrees, plus alpha, which is always greater than or equal to 180 degrees. So this idea of Euclidean geometry is always 180 degrees in a triangle. It's not true anymore. So those are some different properties of spherical geometry, Euclidean geometry. Hope you enjoyed that. Give us a comment on any topics you want to let us go through, and we will.